Okay, so the plan for today is to talk about section 8.5, probability as an application of integration. And there are some, this is something that if you become a math major, you'll probably take a course in. So let's get started. So I want to talk about so-called random variables. And what's a random variable? Well, I'm going to give you examples. So an example of random variable is the temperature. Or maybe the lifetime, of an LED light bulb. Or 3, the number of siblings that you have. Okay, so the first 2 cases are called continuous random variables. Their values can be in some interval, right? A, B. They take place in an interval A, B. For example, the temperature could be any number between minus 40 degrees Fahrenheit and 110 degrees Fahrenheit, and any number in between, any real number in between. Even though when we report the temperature, we're only narrowing it down to the nearest degree, or we're estimating it as a whole number. Temperature is any real number. Likewise, the lifetime of an LED bulb is a real number, and it can lie in an interval of some sort. But the number of siblings that you have, that's a different story. That's a whole number. That's a discrete random variable. And in what follows, I'll largely be considering continuous random variables, okay? So we usually denote a random variable by a capital letter. In this case, I'm going to call it X. Okay, so, and we write A is less than or equal to X is less than or equal to B. So 2 numbers. So for the set of all outcomes, X such that X of X is in the interval A, B. Now, if this doesn't make sense, it will in a moment, okay? It will in a moment. So let me save the screen and clear it. Okay, so here's how it works, right? So every random variable, every continuous random variable X has an associated probability density function, f of X. This is a real valued function, and this is f of X is greater than or equal to 0. And it has the following property, that the integral from minus infinity to infinity of f of X is equal to dx is equal to 1. So the picture you may have is some curve, defined on the whole real 9, and the area under the curve in the sense of improper integrals has value 1. And then we write the probability that A is less than or equal to X is less than or equal to B is the probability of the event of X lying between the values A and B. Like, for example, the probability that the lifetime of a light bulb is between 10,000 hours and 11,000 hours. This would be the integral from A to B of f of X dx. Okay, so this is the probability that X lies between A and B, and that's given by the area under our curve between A and B. So if this is A and this is B, that would be this area here. Okay, so I'm going to give you some examples today, not too many, of distributions. Okay, so let's get started. So my first example, oops, I want to make that black. So example 1 is a so-called uniform distribution. And usually it's denoted like this, U01. Okay, and what it is I have to specify the PDF for this. And the PDF is given by the following function. F of X is equal to 1 if X is between 0 and 1, and 0 otherwise. So this U01 corresponds to the interval from 0 to 1. And what you have is the picture of the graph of the distribution is that it looks like this. So it's non-zero on this shaded region here. And this is a probability density function because the area of the unit square is 1. And by the way, we usually use the word PDF denotes a probability density function, because that's a much shorter way to refer to it. Okay, so what is the probability then of X of a random variable with uniform distribution lying between A and B? Well, that would be the following. It depends where A and B are. So if A is less than B is less than or equal to 1, maybe less than or equal to B, and it's not less than, well, let's write it like this, strictly less than B. Less than or equal to 1, it's going to be given by the area. A and B then would be lying in this interval between 0 and 1. It would be getting the area of this rectangle enclosed by the green segments, and that would be the area of base times height, so it would be B minus A. Now, what if A is less than 0, less than or equal to 0 is less than B is less than or equal to 1? So that would be the case that you would have where A is, that would be integrating, the fact that A would be less than 0 would mean that the only place which matters would be between 0 and B, and you would get the rectangle of height 1 with base B, so you would get B in this case. And likewise, if 0 is less than or equal to A is less than or equal to 1 is less than B, then it would be from A to 1 you would be integrating, and you would get 1 minus A as the area. So that completely determines the probability of a uniform random variable of type U01, that determines the probability completely. Okay. More generally, we have for numbers, I don't know, C less than D, U of CD, the uniform distribution of type CD. That has PDF given as follows. You take C and D. I'm just for convenience putting them on the positive x-axis. And then you have to make a rectangle of area 1. And so let's do that. How do we do that here? Well, what would the base times the height be? It has to be 1. So that would tell me that the height would have to be 1 over D minus C. If x 0 is less than or equal to x is less, oops, not 0. And it would be 0 otherwise. Okay, so that's another example. Okay. A more interesting example is the so-called exponential distribution. Okay, so what does this do? This is something that's actually applied in the real world. It models waiting times. For example, you might own a warehouse and you're waiting for orders to come into the warehouse. And you could ask, how long do I have to wait? And and what is it determined by? It's determined by a constant that you have to choose. So you choose C bigger than 0. And now I'm going to define this as a function of t, because t is time. F of t, in this case, this is the PDF for our exponential distribution. The PDF is given by 0 if t is less than 0, and it's given by c e to the minus ct for t greater than or equal to 0. So this is an exponential function, and for t bigger than 0, it looks like this. It's decreasing, and if for t less than 0, you get 0. So this is what it looks like, and it really is a PDF. To check that, we know this is non-negative, of course, but we have to compute the integral from minus infinity to infinity of f of t dt to show that it's 1. And this is the same because of the way the function is defined as the integral from 0 to infinity of c e to the minus ct dt, which is the same as the limit as, let's say, u goes to infinity of the integral from 0 to u of c e to the minus ct dt. And then when we integrate, we're going to get the limit as u goes to infinity of minus e to the minus ct evaluated from 0 to u. And this is the limit as u goes to infinity So this is going to be, I'll pull out the minus sign, and we're going to get e to the minus cu minus 1. And as t, u, oh, there's a u here, not a t. As u goes to infinity, because c is positive, this first term goes to 0. So you're going to get 1, and that checks out. So we really do have a PDF in this case. Okay, so what I'd like to do is talk about expectation expectation of a random variable. So what is the expectation? So here's the motivation for it. Let's go to the case of a discrete situation. Suppose I give 4 exams, each worth 100 points. So then the average, let's say the exams you get an 85, then you get a 95, and then you get an 80, and then you get a 100, right? So the average would be 85 plus 95 plus 80 plus 100 over 4, which I think gives me 90, an average of 90 it should be. Okay, but maybe I want to weight the exams differently. Maybe if this is exam 1, this is exam 2, exam 3, exam 4, maybe I want to weight the first exam by not 25% of your grade, but maybe just 20% of your grade. So I take 0.2 times 85. So this is the weighted average. And maybe I wanted the second exam to be worth more. Maybe I want it to be worth 30% of your grade. So that would be 0.3 times 95. And then maybe I want the third exam to be worth just 10% of your grade. So I take 0.1 times 80. And then I add to that maybe, so what's left over, I've covered 50%, 60% of your grade, so I have to take 0.4 times 100. And that would be the weighted average. And what is it? So this would give me a value of, if you calculate 93.5, the weighted average, which is different from the average. And so what is the weighted average? Well, you can put on the horizontal axis the weights. And so I would have 0.2, then a point, so the various exams, exam weights. So you would have a 0.2, a 0.3, a 0.1, and a 0.4 here. And then I'm not ordering the weights here. And then you would you plot the exam value, the exam scores. And the exam score here would be according to the weight of 0.2, you would have an 85, you would have a 95, you have an 80, and you have 100. And then you would multiply, if we let the weights be denoted by xi, I goes from 1, 2, 3, 4, and we denote the value of the score, f of xi, is the score at the ith exam. We're taking summation, I goes from 1 to 4 of xi times f of xi. So that would be the weighted average. Okay, so that's in the case of something discrete. What I'd like to do is generalize this to a continuous random variable, and this was all motivation just now. Now I'm getting to the meat. Okay, so so this is the expectation or the expected value of a random variable x with associated PDF f of x or f of t. Let's say f of t. So the expected value is you take x and you put it in square brackets and you put an e on it. And this is supposed to be a weighted average. And by analogy with what I did with the exam grades, instead of a sum, I should be taking an integral over all weights. And then I would get t times f of t. So it's just like I had xi, f of xi, dt. So that's the definition of the expected value. Okay, so what I want to do in closing is do one or more problems. And then I'll close with one more distribution. Okay, so let's do the calculations. Okay. Okay, so let's consider the example. Oops, I don't want that color. Of the uniform distribution of type 0, 1. So remember that f of t then was 1 if t is between 0 and 1 and 0 otherwise. Okay, so what is the expected value of a random variable of uniform type? By definition that I gave on the previous slide, it's integral from minus infinity to infinity of t times f of t dt. But f is only non-zero between 0 and 1, so this would be the integral from 0 to 1 of t times f of t is 1 on 0, 1 dt, and you get t squared over 2 from 0 to 1, and that's giving me a value of 1/2. So the expected value of a uniform distribution of type 0, 1 is 1/2. Let's try another example. How about the exponential distribution? Well, in that case, f of t was equal to 0 if t is less than 0, and c e to the minus ct, t is greater than or equal to 0. So I have to compute the integral, the expected value of an exponential random variable would be the integral from minus infinity to infinity of t f of t dt, which is the same as the integral from 0 to infinity of t c e to the minus ct dt. So we're going to have to compute this integral. And this is going to be an integration by parts situation. So let me make some space by clearing the slide. Okay. Well, first let me consider the situation of the indefinite integral. That would be c t c e to the minus ct dt. So I would let maybe u equal c times t. Here, just c is a constant. Treat it like any old constant. Du is c dt. dv is what's left over, which is e to the minus ct dt. So v is equal to minus 1 over c e to the minus ct. And we're going to get u times v, which is looks like it's going to be ct times minus 1 over c e to the minus ct. So there's some cancellation, and minus t e to the minus ct. Minus negative, so that's a plus, the integral of, when we multiply these two terms together, v and du, we're going to get, with the sign change, we're going to get e to the minus ct dt. Should appear, and then what does that give us? That gives us a value of, the first term is, again, minus t e to the minus ct. And then lastly, we get we get plus, or it's actually a minus 1 over c e to the minus ct plus some other constant, let's call it d, because we already used c up. Okay, so that's the indefinite integral. So now we have to take the indefinite integral and evaluate it from, so remember, going back to the improper integral that we're interested in, we have to calculate this. So let me just use some variable x going to infinity of the integral from 0 to x. of t e to the minus ct dt. So now, if we evaluate, so I made some space, and so I'm going to try to substitute the limits of integration in now. So we're going to get the integral, the integral from 0 to x of t e to the minus ct dt is going to be given by minus t e to the minus ct minus 1 over c e to the minus ct from 0 to x. Okay, so what does that give us? When we evaluate it at x, let me factor out a minus sign. When we evaluate it at x, we're going to get x e to the minus cx plus 1 over c e to the minus cx, and that would be the evaluation at t equals x, and the evaluation at t equals 0 would be 0 plus 1 over c. Okay. All right, so now what happens as x goes to infinity? I'll just put that here. Well, x, since c is positive, this multiplication would be x over e to the cx, and by a L'Hopital's rule argument, this is going to go to 0. So this term goes to 0. This term goes to, also goes to 0 for an easier reason even, and you're going to be left with 1 over c. I believe that's right. So in summary, what you get is that the expected value of the exponential random variable is 1 over c, if I haven't made any arithmetic mistakes. Okay, so I want to briefly, at the end of this, this lecture today, talk about something called the normal distribution. This is something you are actually all familiar with in one way or another. So what is that? There's a so-called bell curve. So what it looks like is it's a curve, and it depends upon two parameters, two real numbers. So two parameters. The first parameter is called mu, and the other is called sigma. So I don't know, I might have not pressed the pause button enough times or too many times, but in any case, I want to talk about, I hope I haven't said this already, otherwise my lecture is like really goofy. I want to talk about the bell curve and as an aspect of it, the area. So the number mu is the expected value, and the number sigma is called the standard deviation, and it represents this, how spread out the bell curve is. And it turns out that if you're within one standard deviation, that's between mu minus sigma and mu plus sigma, then 68% of the area under the bell curve falls within those values. And so it's known for IQ, for example, IQ scores. The mean is 100 and the standard deviation is 15. So if you're between 85 and 115, 68% of the entire population is supposed to reside between those two values. Okay, that's enough.